what they can do is they can kind of process their local information and communicate with their neighbors, right? So that's a fairly standard setup. I think after 2 days of it, it's not news. And so what we want to do is look at a very simple rule and then actually and show that it has a cute rate of convergence. And the cute rate of convergence looks interpretable, so then we feel happy as a theorist because we can pat ourselves on the back. Okay, so we have n nodes, and they're m hypotheses. So this is, in particular, for the clean version of the proofs to go through, we need the parameter space to be discrete. Continuous parameter spaces, I think, are doable, but the communication aspect becomes a little trickier. We have these observations xi at node I at time t, which are taken iid from some distribution, which is known only to that node. But those distributions for each node I, the node knows its own distribution. So it says, like, if the state of the world was theta 1, then it would have fi, not conditioned, I guess, but for theta 1. So in particular, I don't need to know, they don't know what the other sensors are doing, or what their observation distributions are. And we have a fixed known global parameter theta star. It's one of these m hypotheses. Might as well think about it as the last one for now. And right, so this is the distribution, as I said, of xi at time t is this fi for theta star, for the true parameter, which is, of course, one of these distributions. Okay, so we want to infer what the true theta star is. We want everybody to learn what the true theta star is, and we want to know what are conditions under which that's possible. So obviously, we could compare this to the centralized problem, where I have all the observations in one place, and then we pretty much know what to do. It's, as long as theta star is globally identifiable, that is, the distributions, the product distribution across these nodes are different for each of the hypotheses, then we just get exponentially fast convergence to the true hypothesis based on the worst case KL divergence between any two pair of hypotheses. Right? So what can go wrong? What can go wrong with just local observations? Right? So what can go wrong is the following. Let's consider a toy example. There are two types of sensors. There's a color sensor and an intensity sensor. And node 1 has a color sensor and node 2 has an intensity sensor. And they want to decide between light or dark, red or blue. Right? If they only take their own observations, they're unable to distinguish between these four hypotheses because they're individually, the hypothesis is not identifiable at each node. Right? So you do need to have some, in this case, we need to have some sort of communication. So that's really what can go wrong here is if you have crappy sensors who can't really identify the parameter, then they need to talk. Okay. So let's look at, for each node I, then we have to kind of look at this, we have to partition the set of hypotheses at that node into equivalence classes of nodes, of hypotheses with identical distributions, right? And so in particular, we're interested in all of the hypotheses which to node I are confusable with theta star, the true hypothesis. Right? So these are all the guys that I can't tell from the truth if I'm node I. Right, so that is to say, if theta is in this capital theta I bar, this set of equivalent to theta star thetas, equivalent to theta star thetas, then they're observationally equivalent, right? So I have to be able to get, if I'm node I, get some information from somebody else to help me disambiguate between this set. And so basically, it seems clear then that with this setup that basically you need to have theta star be in kind of the intersection. You can't have two hypotheses which are indistinguishable for all nodes because then we're still back in that same unidentifiable collection. So this is kind of the identifiability condition condition that is necessary here. All right. Okay. So now that I've set up all this problem, so it's just going to give you a learning rule without any motivation at all. So what we'll do is we'll start everybody out. We'll start with a sort of estimate of a size of theta, so m-dimensional vector, which is essentially my belief about which of the true hypotheses is correct. So these will be a probability distribution. I'll just treat this as a prior for a Bayesian inference step locally. I get an observation. I'm going to draw my xi at time t. And then I'll just do a Bayes update. I'll just compute Bayes' rule to figure out what is my posterior belief about the true hypothesis given what I saw before. Now, so if I have two hypotheses are observationally equivalent to me, then they're going to get moved by the same amount. So that, like I've not changed my indistinguishability problem here just with this local update, obviously. OK, so then what I'll do is I'll just send to my neighbors, I'll send them my belief. Like, this is what I think about thetas. What do you think about thetas? And then you send me your belief. And then if we're in a current political climate, we just argue. But let's say we're trying to actually do some learning. So I'm going to get all my neighbors' observations. And then now what I could do is like do the regular consensus thing where I just average the beliefs. That would still be a probability distribution. I would need well-motivated, blah, blah, blah. Seems like the thing we normally do. But actually, I'm just going to do a weighted average of the log beliefs and then kind of exponentiate and rescale to get it back to being a probability distribution. Why am I doing that? Because it sort of makes more sense. I'm trying to merge these probability distributions, so I should think of them as merging log likelihood ratios. I'm trying to get a good handle on how the likelihood is evolving. And then you can have some weights like you do in a standard consensus problem. And then we can say, OK, what do the weights need to satisfy to get something nice? OK, so it's basically like doing average consensus, where except I do a Bayes step first, because I have observations over time. And then I do an averaging in this log belief space, like log likelihood space. All right, and then repeat ad nauseum. Right, so just to put it in a boxes and arrows version, we have some local observations. And then so it's a Bayesian update and averaging these log beliefs. I call this sort of pseudo-Bayes. It's like Bayesian inference done by people who don't know anything about Bayesian inference. OK, so back to our example. So now if we just stick a little bit of weight, some small weights here, well, this is a big weight, but this is a small weight, for 2 to influence 1, then we can rerun the simulation, no problem. The color sensor, who before had no idea what the difference between dark and light was, now suddenly knows something about dark and light. And you'll get what looks like pretty fast convergence. These are the the posterior probability. Well, I shouldn't call them posterior probabilities, but those are beliefs over time of on the 4 hypotheses, and the wrong ones die out pretty fast. Okay, so now to what is a theorem we can say about this sort of thing, right? So we need some assumptions. What time? Is there a clock? Okay, good. So for every pair of hypotheses, or every hypothesis different from the true hypothesis, then one node needs to be able to distinguish that true hypothesis, the true hypothesis from that hypothesis, right? So that makes sense. So somebody knows the difference between the truth and any particular single other hypothesis, but they might be confused about the truth and a bunch of other things. And that's basically encapsulated by saying the KL divergence is bigger than 0, which just means that locally they could make that they could solve that binary hypothesis test. The second is that okay, this seems standard. This matrix W is stochastic and irreducible, but it doesn't have to be doesn't have to correspond to an aperiodic Markov chain or anything like that. So we don't need nice, even more nice properties of W. We'll get back to that in a little bit. And I guess the last thing is you can't start out, maybe back to our current political climate, you can't start out having 0 belief in the true hypothesis. Because if you do that, then nobody's going to be able to convince you of anything. But maybe the regular averaging rule would work there. So we need this, otherwise taking log of 0 makes bad things happen. Yeah?
Why do you need it for all I? Is it enough that some I?
It's because of the update rule. We could fudge it by we could either have a weirder looking update rule, which means that we don't have to take logs of zeros, or we make this assumption and then don't have to take logs of zeros. So it's sort of like, where do you want the annoying bit? This is, put in an assumption. Right, yeah, if you just put a delta on the update rule, everything works out and everything is fine. So, totally reasonable. All right, so the quantity of interest that's going to be of interest here is what we call network divergence, which is just the eigenvector centrality weighted KL divergence. So we can define it between theta star and any other hypothesis theta, or any pair of hypotheses. And it's just the weighted sum of divergences across all the nodes. So because one of these divergences has to be positive, this number is positive by assumption. But a lot of them could be 0 because a lot of nodes could be too dumb to distinguish between theta and the true hypothesis, theta star. So this eigenvector centrality is the same standard thing. I just look at the eigenvector corresponding to eigenvalue 1 for the Markov matrix. Okay, so what can we say about convergence? So this is like a frequentist analysis of a pseudo-Bayesian procedure. Let theta star be the unknown parameter, and we have those 3 assumptions. Then every node estimate of it's like belief, I should really say belief, of a theta different than theta star converges to 0 exponentially fast. And it converges exponentially fast at a rate, of course, that is the network divergence. So this is what I mean by network divergence. Nice, cute formula. So we feel happy as a theorist. It turns out that it is, in fact, the true rate of convergence. This is P almost surely. But this is the distribution, the probability space we're considering. So okay, so good, done. All right, now what about an example? So we can just do a grid and put on some weights, which is like 1 over the degree, and calculate the eigenvector centrality. And lo and behold, it turns out that node 5 is more influential than the other ones because he's in the middle. So that makes sense. And then you can do some experiments. You can see everybody is dumb and cannot tell anything about any. Suppose that only the top guy can be able to tell theta from theta star. And everybody else cannot tell any theta different from theta star. They think all hypotheses are the same. So basically, they're getting garbage observations, just noise. And we can see, indeed, that you get faster rate of convergence when you put when the influential guy in the social influence sense is also the smartest guy in the sense that they have the best scale divergence, right? So that makes sense. Okay. So this is the theorem again. So we can also get a lower bound on the rate of convergence. That is for this particular algorithm. So it's maybe not exactly exciting lower bound in the world of lower bounds. But we also can show that essentially the rate of the probability of the whole total mass of non-correct hypotheses is also going to 0 at this rate. We actually have a large deviation analysis of this rule, but it was ugly and I didn't want to give it in a talk, but it's in our paper, which will appear eventually in the IT transactions. Right. So in particular, if we define kind of the L1 deviation, so the total variation distance between the belief in the hypothesis and the atomic distribution on theta star, so that's like the asymptotically the thing you're converging to, and we can look at the sort of large deviation property of that, then we get a lower bound that's also kind of the worst case over all pairs of hypotheses. Whatever the worst is, that's the lower bound of the speed at which this thing goes to 0. So this is really the quantity of interest, which is maybe not surprising, but is also surprising to me still. So maybe I'm just slow. Okay, we can go back to our grid. We can go back to our, essentially color versus intensity hypothesis space here. Now, if we look at that example again, and we actually make the W matrix periodic, it's fine. It's just that the it looks a little bit fuzzier, but the rate of convergence is still there. So this is maybe in contrast to some other types of consensus methods. But I mean, that's sort of a mathematical oddity, not. You can see how the mixing time of the matrix is going to affect the rate of convergence here as well for the aperiodic case. Okay. So in addition to that large deviations result, which I didn't really mention, we also have this sort of related concentration result, which basically shows that the posterior belief, the chance that the log, the log belief at time t deviates too far from the network divergence is bounded by some exponentially decaying thing that is e to the minus t with some stuff. But in order to do that, we need a kind of extra assumption, namely that the log likelihood ratio between any pair of hypotheses is bounded. We can relax this. This is for technical reasons, but we can sort of relax this, but it's not really super interesting. Okay. Sort of connect this to a couple other things that people have looked at. There was a sort of earlier, the reason we started working on this was this earlier paper by Jadbabai et al. That basically looked at kind of linear averaging of the beliefs. Had this Bayes up step in linear averaging of the beliefs, and they provide an upper bound of the rate, and we can actually show that our learning rules converge strictly faster than theirs. So it's good. We made an improvement. There's also sort of another paper which looks at this case where W is doubly stochastic and shows a lower bound for the rate of identifying the true hypothesis, and our rule actually achieves that same lower bound. So it's sort of like you can show that that's kind of tight, which is nice. We are okay. So then. And you had another paper which looks at continuous parameter spaces, and which I think is an interesting extension here, because the communication thing is now, if I send you my belief, I'm just sending you m numbers, so that seems okay. But if I have to now send you a density, that seems weirder. So we'd have to figure out something else to do there. In addition to the result, the sort of main result about the network divergence characterization was simultaneously proved by two other people at the same time, two other groups at the same time. So one Sharampur et al. And the other Nedic, Olszewski, and Uribe. And they kind of connected it actually to a different distributed stochastic optimization problem for irreducible and aperiodic W. So there's kind of a different interpretation. You can come at it from a different direction, where I just sort of said, here's a rule, let me analyze it. Okay, so I think that's a bit all I have. Very good. The combination of a sort of local Bayesian updating and averaging, this nice quantity network divergence, which I would hope appears somewhere else, somewhere interesting. And we get this sort of posterior consistency style of a result saying the parameter is still identifiable under this procedure. A bunch of things that I'd like to kind of look at in the future would be, potentially, would be things like continuous distributions. I think it'd be interesting if you have more complicated inference tasks than just a finite discrete hypothesis test, which you would probably get in more real applications. You would want to, you'd want to be able to sort of compress the densities and send and propagate those in a sort of nice way, especially if you're doing this over like a real communication network. Maybe there's some more connections to distributed optimization, the topic of this workshop. One particular interesting idea might be to connect this to kind of like coordinate descent methods where I kind of maybe sample from the posterior or sample from my belief and only send you samples from my belief, which could be interesting, and also could have some connections to doing things with privacy, which I also am interested in. And then of course there's like the big like, you know, impossible problem where it's like you just have this sort of general stochastic process and you're taking observations and you want to do some sort of distributed filtering or something, which seems hard. Yeah, so thanks. Maybe I should have put some proofs in.
Yeah, so that was quick.
Sorry, I got all these warnings about how much time we were supposed to spend, and then I kind of got freaked out.
Okay, so we have 15 minutes for questions.
Oh no, okay.
Or whatever questions we have, and then we can follow that up with a short break before the next talk. Yes. Bud?
Thanks. So there seems to be an analogy between gradient descent type of methods and the Bayesian update rules, right?
Right.
So is there any way to sort of have different update rules that are maybe based on acceleration or something else so that you can learn a bit faster?
Yeah, I guess that's what this sort of is. Is like maybe I could. So I started out with this. Let's do something sort of pseudo Bayesian, and then of course then there's smarter things to. There should be smarter rules than that. But it's. I mean, the other thing I'd like to be able to do is prove like a real lower bound, like a minimax lower bound on estimation in this problem, but
Stochastic gradient lower bounds.
yeah. So those techniques I think might be interesting to look at in this context.
So regarding the extension to continuous distributions and continuous inferences, how would you possibly tackle that problem? Because I think there are multiple approaches.
Oh, there's tons of
Dating back
approaches.
to, like kernel density estimation, so many different things.
Yeah, so I could, you know, the first thing I would sort of look at and probably then run away in horror screaming from is like, let me just do, you know, some nice kernel density estimator and then propagate the weights and the locations of the kernel points and then try and see how fast that has to scale up to get accurate density estimation and then try to make all the error bounds work out nicely. That doesn't. That seems like on paper, that seems like it might be doable, but it also seems like it'd be just very messy. You could, for nice classes of distributions, you could do something like project the density that you estimate onto a nice function class with a nice parameterization, and then send that, which is maybe a little bit more of a parametric approach than the kernel density estimator. And that might actually be better.
Other questions?
For that latter, were you thinking something like function classes that has sufficient statistics, like that would serve as conjugate models in the Bayesian sense?
You could do that, yeah, there'd be that, or just a purely function analytic, you know, kind of like, here's a nice class of, you know, family of linear space of you know, polynomials or something. I don't know, do something with that. But yeah, one way or the other. I think one is sort of thinking about it as a probability problem and caring about the probability, and the other is being like, just a shape. I want to get the shape right.
Other questions? Okay, let's